Section 2.4 kind of puts together the rest of the chapter in chapter 1 that we've talked about. So we spent the first day in chapter 2. Spent the first day of chapter 2 talking about graphs and ways that we can display qualitative data. And then last class we talked about ways to display quantitative data. But the caveat to all of this is we got to make sure when we're displaying our data that we're displaying a good graph. Because statistics often gets a bad rap for being able to manipulate data to support any position. One of the main ways that statistics will end up doing this is through graphics. So think of like opening up a newspaper or a magazine, and the graphic designer decided to go for something cute rather than effective. And we've accidentally misrepresented our data because we've made a misleading graph. So there's two ways that a graph can be a bad graph, if you will. We'll call them misleading if it's an unintentional creation of a misleading graph, being like a graphic designer caring more about the way that it looks, making it look pretty than making it look effective. Or deceptive if you're really trying to skew the reader's ability to understand what the graph is showing you. So we're going to see 4 examples of what a scenario and then a bad graph representing that scenario and then a good graph representing the scenario to try to see what some of the pitfalls are for you as a consumer of information and us as students of statistics that we're going to have to make these graphs for our project, right? We want to make sure we're making good, not misleading, and not misrepresentative graphs. So for example, a home security company located in Minneapolis develops a summer ad campaign with the slogan, "When you leave for vacation, burglars leave for work." According to the city of Minneapolis, roughly 20% of home burglaries occur during peak vacation months of July and August. The advertisement contains the graphic shown. All right, so the company, or I guess what is it, the city home security company, is trying to get you to understand that you probably need a home security system, so they put this on an ad in a magazine. Why is this a misleading or deceptive graph? Tell me more. What about the months?
It doesn't tell you how much for each month.
Doesn't tell you how much for each month. It has a category for July and August, and then like literally other months. How many months are in the other months section? 10. So we have 2 represented here and 10 represented here. Is that a good representation of this graph? No. The bigger problem though, you're not wrong. That's a problem. The bigger problem though lies with this. Yeah, what do these percentages add up to? But when we're talking about the percent of burglaries that occur in which month, they should add up to what number? 100. This is misleading because the main problem, besides the one you guys said of like, where are the other months, the percentages don't add up to 100. If we are talking about a relative frequency or a percent of all burglaries, and we're showing all of the months, they should add up to 100. So this is misleading because it makes it look like there's a 12% difference in July and August in the other months. That just doesn't make sense. So instead, the corrected graph that they could still use in their ad campaign would look like this. What's better about this graph? It shows me all of the months, but what conclusion can I still draw from this graphic that we were trying to convey in this graphic without misleading me? If we're still looking at July and August compared to all of the other months, and we added those 2 together, it would still be rather high in the amount of burglaries that are occurring in these months, right? We can still see what point they're trying to prove in this ad campaign, but it's not as drastic as they showed originally. It's an ad campaign to try to get us to use their services. So of course, they're going to make it look like what they want it to look like. So here's what we would say for what does the graph convey? It does convey that there is a spike in robberies in July and August, but it's definitely not as drastic as the first graphic. And if we were to get all of the percentages, they would add up to 100. Let's look at the second example. A national news organization developed the graphic shown to illustrate the change in the highest marginal tax rate effective January 1st, 2018, comparing 2017 and 2018, basically. Why might this first graphic be considered misleading or deceptive?
You start off at 36 instead of 0.
Absolutely. This is a problem. Because we're starting off at 36 and then counting by 1, we're seeing a drastic change in these numbers. When in fact, if this was like, 39.5, this is at 37, that's only a 2.5% change. Does this look like, to the person who's reading this, a 2.5% change? No. So that is definitely a problem. The scale, I spelled the word scale wrong. Let me try that again. The scale doesn't start at 0. If we were going to start with the x-axis being 36, we would probably want the next line to be a multiple of 36, which is still an ineffective way to show this information. So instead, if we look at the corrective graph, what does this graph convey that the original graph did not? Because now I'm starting at 0, going by 5s each time. If this national news organization was trying to show us that there was a decrease in the highest marginal tax rate between 17 and 18, do we still see that decrease?
Yeah.
But does it look more effectively like 2.5%? Yes, so it more effectively tells the information because the difference in the tax rate looks more appropriate. So these first two are examples of traditional mistakes that we would see in graph making. On the back, what we're going to see is when we as a statistics, company that's producing quality statistics, gives our data to a graphic organizer, and the graphic designer decides to make them look cute. There are some problems with graphs that look way too cute. Let's look at the graph on the back. The most popular team sport in the United States is basketball with 24,917,000 participants. The third most popular team sport is soccer with 11,913,000 participants, which is about half of basketball's participants. To illustrate the difference in popularity of basketball, a publication produced the pictograph graphic shown below. What's wrong with this? Why is this misleading? It does start at 0. Oh, you mean like this doesn't start away down at 0? That's a problem, right? But remember, we're trying to say that soccer has about half the participants as basketball. If you were just reading this thing, would you think that is half? No, because it looks like a quarter to me, basically. But what they're trying to do is show you this one's about 12 million and this one's about 24 million. But does that come across in this graph? No. So the problem is the basketball is way too big. The basketball is way too big because it's more than twice the size. This is why I was making such a big deal when we were drawing our graph. The widths need to match when we're comparing two things together. This is essentially a bar graph, but a bar graph with different widths. So it makes basketball look way wider, thus covering more area than soccer. Misleading. Very cute. Misleading. So instead, if we still wanted it to be cute, like our graphic designer that we give our data to is putting our findings in a publication of some sort, this would be a more appropriate pictograph. Why is this one more appropriate? They have a key, absolutely. Definitely having a key is super helpful. I can also immediately see that since this takes 1 line and this takes 2 and a little bit more line, I can more accurately see that soccer has about half the participants than basketball because it has half the number of soccer balls-ish. It's definitely more clear. So I agree with you. There is a key. That's super helpful because now I have more accurate numbers. And also now soccer looks like half. Somebody in my first period class asked where'd I get these numbers from, and I forgot to put down where I got them from, but it's in our textbook. I will go look in case somebody was like trying to not agree with basketball versus soccer. I didn't get these stats, I'm just reporting them. So again, if we're trying to make graphs look cute, we can fall into some other traps. Example 4, educational attainment. The pie chart represents the educational attainment, which is the level of education, in 2021 of adults 25 years and older who are U.S. residents. They surveyed this many people, and this was the highest amount of schooling that they went to. So not finishing high school only, doing some college, finishing an associate's degree, finishing a bachelor's degree, finishing a graduate degree. I've then calculated the the frequency distribution here, or relative frequency, I guess, yeah, of each of these. So the percentage of the total. We hand our data to somebody who makes the following pie chart for us. Why is that first pie chart misleading? There aren't any percentages. That's definitely a problem. Let's put that down. Pie charts are helpful, but it is better to have numbers on there so we can actually compare numbers. Why else would the first one versus the second one be misleading?
It might be me, but I can't really interpret which section is bigger than the other.
That's exactly right. She goes, it might just be me. It's not just you, it's everybody. We can't really interpret which one's bigger or which one's smaller, especially if we focus our attention on some college. That's this one, right? It's about 15%. Compare that to graduate degree, which is 14%. Those sizes should be very similar, right? Does that size look like this size? No, that's super misleading. I think there would be like nobody getting a professional or graduate degree. When we take this 3D image and we make it flat, those two pie pieces look way similar now, right? That's a more accurate understanding of this graph. So the 3D, while it's cute, it distorts the sectors, the pizza pie slices, if you will. It distorts how much it looks like each pie slice got. So by putting it in 2D, one, we get the percentages back on this one, which is definitely better. But we can also, in the 2D, we can actually compare sizes without a distortion. So our brain will naturally make the correct assumptions when it's in 2D rather than 3D, just basically because we're always comparing sizes of these pizza pie slices. So on your homework today, it's going to be showing you some bad graphs or asking you what's wrong with graphs or when graphs would be appropriate or inappropriate for data. So make sure that you can, as a consumer of information, know when you're presented with a bad graph and maybe how to make it better.